on to chemistry, where in this video we are going to wrap up the unit of gases, starting with the ideal gas law, which is possibly the most important gas law, as it allows us to utilize it in the most various of situations. And so looking at the ideal gas law, it has all the variables that we discussed in the last video: pressure, volume, how much gas is present. N is going to stand for the number of moles of gas that you have, as the amount of gas in question is certainly a factor. And then T for temperature. But what is this R? Well, R is our new guy. And R is what is known as the ideal gas law constant. It's a number that never changes. When these gas laws were starting to be explored, right, when they learned the different relationships between each of the variables, and then when they smushed them all together, they realized that if they took the pressure and volume divided by the number of moles, or the amount of gas, and the temperature, in any gas, any situation, it always came out to the same value. And depending on your unit of pressure that you're using, that is going to determine what your R value actually is. Usually you're in ATM, and so the R value that you're going to see is 0.0821. Look at all the units here. Liters, which is your volume, times ATM, which is your pressure, divided by MOL, moles, which is your N, and then K, which is Kelvin for temperature. Or if you've got kPa or millimeters mercury, you're going to see that you have different R values there. So all you got to do is just double check what your pressure unit is and utilize the correct R value there. So now let's go ahead and tackle our next example question in your notes. We are utilizing the same notes and slides from the last video, but feel free to click on those links down below if you're watching this on YouTube. So example 7, what is the pressure in ATM exerted by a 0.978 mole sample of oxygen gas in a 6.8 liter container at 28 degrees Celsius? Just like in the last video, they're giving us all of the variables except for one. We're looking for pressure. And because it says it wants it in ATM, well, we might as well utilize the R value that utilizes ATM so that we don't have to do any converting in the end anyway. Aside from that, always double check to make sure that your temperature is going to be converted to Kelvin. Here we're starting out at Celsius, so we do have one preliminary precursory step that we have to do. Another note that I did not say a second ago. Look at the volume unit of your R constant. It's liters. If they ever give you your volume in anything that is not liters, you have to convert your volume to liters. Otherwise, you'd have to convert your R values as well. So watch out for that. Always pay attention to units. Here we go, solving example number 7. Example 7 reads, what is the pressure in ATM exerted by a 0.978 mole sample of oxygen gas in a 6.8 liter container at 28 degrees Celsius? We are going to approach this problem just like we did all of the other gas laws in the previous video. We are going to outline all of our variables, and we're going to plug and chug. The ideal gas law, probably the most important, also probably the easiest to solve because there's no division sign in the equation. So it really is as simple as plugging in all of your variables and dividing by everything that you don't want that is attached to the variable that you're looking for, which is very, very, very simple. So let's go ahead and write down what we got. We're looking for the pressure, and we have 0.978 moles. Moles is your amount of gas. It must be in moles. If it's in grams, you have to convert it. Of oxygen gas in a 6.8 liter container, so that's our volume. As we said in the clip before this, your volume must be in liters because your ideal gas law constant also includes liters. At 28 degrees Celsius. And so we're looking for pressure, but the variable that we're missing is R, but we're not actually missing it because it is a constant. And because our pressure is, the pressure that we're looking for is in ATM, we're looking for it in ATM, which means our R constant needs to be the one that utilizes ATM, which is 0.0821. All right. Last thing we need to do is make sure that our temperature is in Kelvin. So we're going to add 273, which is going to give us a nice Kelvin temperature of 301 Kelvin. All right. Now we're going to set up our equation. PV equals nRT. We are going to manipulate the equation to solve for P. So we're going to divide by V on both sides. So we get P is equal to nRT over V. You have all of your variables lined up on the left.
Therefore, the only way to mess this up now is if you put the wrong things in the wrong spot. So plug it in your calculator. And we're going to round this guy to 2 sig figs because that's the smallest amount that we started with. And so our answer is 3.6 ATM.
Example 8 is solved quite similarly to the previous example, and so we are going to solve that on the board as well here in the next clip. What is the volume in liters of a 4.86 mole sample of chlorine gas at 14.2 degrees Celsius and 0.467 atmospheres of pressure? We're looking for volume. They give us all the variables, right? They didn't explicitly give us the R constant, but it is a constant. Therefore, it is always the same, never changing. And because our pressure unit is in ATM, we are going to utilize that first R value that was in our slides, 0.0821. And so we will solve example 8 now.
Example 8 reads, what is the volume in liters of a 4.86 mole sample of chlorine gas at 14.2 degrees Celsius and 0.467 atmospheres of pressure? Same exact setup, we're just looking for a different variable here. Here we are looking for volume. We have 4.86 moles. We have 14.2 degrees Celsius. And we have a pressure of 0.467 ATM. Just like last time, we're missing 2 variables, but we're not actually missing this one because this is a constant. Therefore, we always have it. And because our pressure is in ATM, we're going to use the R constant that also utilizes ATM, which is 0.0821. Like I said, it is the most common one that you're going to utilize. Just be prepared to utilize the other R constants if your pressure is something other than ATM. So we're going to manipulate our equation. PV equals nRT is our original. We're looking for volume this time, so we're going to divide both sides by pressure. And before we go to plugging and chugging in our values, make sure that your temperature is in Kelvin. So we're going to add 273 to this guy. We did not forget that one. And so our Kelvin is 287.2, like so. Now plug and chug. And keep in mind your answer is going to come out as liters. Look at this, it's like we're actually solving the problem together. I hope you're plugging in the calculator right now. And the answer you get is 245. Let's see, we started with 3 sig figs across the board, so 245 liters.
In example 9, we'll be utilizing the ideal gas law to determine and calculate the molar mass of a substance. And if you have the molar mass, well, then maybe you can identify what this substance actually is. Not a definite outcome, but it is possible, certainly. So let's see the information provided. The density of a gas is measured at 1.853 grams per liter at 745.5 millimeters mercury and 23.8 degrees Celsius. What is its molar mass? Well, we're going to actually describe 2 different strategies that you can implement here. The first one is a little more complicated, and the second one is a definite shortcut. So we'll describe that here in a second. First thing, convert your pressure to ATM. You do not have to do this. If you have and know all of the R values for the different pressure units, well, then there's no point in doing this. Because our problem was giving the pressure in millimeters mercury, we can just use 62.4 as our value for R. But also make sure that your temperature is converted to Kelvin, as it says. They are not providing volume, and so what we can do is we can assume that it is standard, okay? Which means we're going to be dealing with 1 liter. We're assuming that we're dealing with a 1 liter situation. And so we are going to utilize PV equals nRT, aka Pivner, to the ideal gas law to solve for N, which is going to give us how many moles of gas we have present. And if we have the moles, and then we have the density, 1.853 grams per liter, we can determine how many grams we actually have in this amount of space. And if you have the moles, and you have the grams, well, try to fill in the blanks here. You can convert your moles to molar mass from that calculation that you just did. But I don't like that method as much as this shortcut. Here is an equation that is not commonly known, I would say it's a more obscure and it doesn't have a name to it, but it is a shortcut for sure. Molar mass is equal to the density times the gas constant times temperature over P. The way I like to describe this is dirt over P. If any of you have any cats at home, hopefully they're going to the bathroom in a litter box, and if you've ever observed your cat after they settle their business in there, what do? Well, they brush their dirt over their pee or poo, whatever they're producing in there, okay? But they usually brush the dirt. They don't want to, they're hiding the evidence, okay? And so we're going to utilize this to solve example 9.
In example 9, we mentioned 2 different ways we could approach this. We are going to utilize the shortcut method. I call it a shortcut method. Not too much shorter, but it's easier. Molar mass is equal to dirt over P, the density times your gas law constant times temperature over pressure. Okay, so let's look at the information that they've given us. We are going to look for the following variables on the other side. If we have all of this information minus our one variable that we're looking for, molar mass, then we are good to go to plug and chug. So reading our question, we have a density of 1.853 grams per liter. It is super important that that is grams per liter. Just as we said, we are going to be utilizing the gas law constant, and keep in mind that your gas law constant's volume is in liters, so it must be grams per liter if anything. And the pressure is 745.5 millimeters mercury. And our temperature is 23.8 degrees Celsius. So this is our first example where our pressure is not in ATM. Totally okay to convert this guy to ATM. If you don't want to do that, then just look at what the R value is for something that is in millimeters mercury, which is going to be very, very common value that you're going to see. Millimeters mercury is probably the second most common unit of pressure that you utilize. The R constant for that is 62.4. So we keep reminding you to do this. Check your pressure unit and then pick your R constant from there. Or, as I was taught in school, you can convert anything to ATM and then still utilize that 0.0821. Whatever floats your boat. Convert your temperature to Kelvin. So that's going to be 296.8 Kelvin. And this one is already solving for molar mass, so truly this is the definition of plug and chug. Density times R times temperature divided by P, and let's see what we get. And we get a molar mass. And let's see, we're going to keep our answer to 3 sig figs is what we got. So we got 46.0 grams per mole.
We have a couple more named laws, aka famous people that got to put their name on a law for themselves. And this first one is another real big obvious statement. And Dalton gets the credit for this one. Dalton's law of partial pressure. The total pressure of a mixture of gases is the sum of each of the individual pressures. Mind blowing. 1 plus 1 does in fact equal 2. 1 plus 2 does in fact equal 3. Dalton, oh my goodness, brain blast. So mathematically what this looks like is your total pressure is equal to pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3 plus however many gases are on there. You add them all together and that's your total pressure. Well, how do you find a partial pressure? That's not really what we're going to be concerned with here, but a partial pressure is determined by what is known as a mole fraction, or they utilize a concept known as the mole fraction, which is not something we'll describe in this video. A very cool concept, but not something we'll describe in this video. So let's see what a couple of these examples could look like. Well, they could be super simple like this one right here. If there are 3 gases in a tube with a total pressure of 5, they didn't even give a unit, 5, let's just say ATM, of 5 ATM, let me add that right here. Look at this, editing on the fly, of 5 ATM, and the first 2 gases each exert a pressure of 1 ATM, 1 plus 1, and there's 3 gases, and it's a total pressure of 5 ATM. Well, how do we get 2 to 5? Oh my goodness! The third gas has a partial pressure of 3 atm. 200 IQ. Insane. So that is a much simple, or the most simple way of looking at Dalton's law of partial pressures. So let's look at this next example. Example 10. A sample of oxygen was collected using water displacement at a pressure of 700 millimeters mercury and at 15 degrees Celsius. This simply means that the gas was produced with a reaction inside a vessel of water. What's important here is that the total pressure, 700 millimeters mercury, is a sum of the gas that we're looking for and the water that it is in. The beautiful thing is that someone has already done all of the work for us and calculated what the partial pressure of water is at every temperature. And so because it tells us it's at 15 degrees Celsius, we were able to do a quick little research, Google on the web, and find out that the pressure of water at 15 degrees Celsius is 12.8 millimeters mercury. So that's the pressure of water. And the 700 millimeters mercury is simply the total. So if everything adds up to 700, 700 minus 12.8, that will give us the pressure of oxygen, the partial pressure of oxygen. Bam, bam, boom. Not too difficult there. Before we discuss our final named law, let's discuss a couple of terms. The difference between diffusion and effusion. If you've taken biology in the past, well then hopefully you've heard of diffusion. Diffusion is the movement of different particles within your body, or any organism's body that you're discussing, looking at, studying, whatever. Diffusion for gases, it's when they move from areas of high concentration to areas of low concentration, which is just how it works in biology. It always goes from high to low. It's like a waterfall. Water is high amounts up here, and it always falls down. It's very hard to reverse the flow there. And so the gases essentially are just getting as far apart from each other as possible. They will evenly disperse in whatever container they are in. Effusion is when gas is escaping from a hole. The best example I can think of here is you're driving your car, you're driving through a construction site, and oh no! A nail punctures your tire. Well, your tire doesn't typically just explode from that single puncture. Air leaks out. Well, what's happening is the gases are randomly moving, but when they encounter the hole, they of course fly out. Well, this next law that we are going to discuss is Graham's law. And Graham's law is a very, very fancy way of saying that the smaller the gas is, the lighter the gas is, the more quickly it will escape the container that it's in. To put it in smart brainiac perspective, the rate of the effusion of a gas is inversely proportional to the square root of its density or molecular mass. Like I said, fancy way of saying, if the gas is thick, with 3 C's, the longer it will take to get out of the tire, balloon, whatever's leaking out of. The bigger you are, the slower you are. Kind of like how it is on a football field or any sports field you're looking at. The bigger you are, you're not going to be able to move as fast, typically. And so, the smallest gas is going to escape the quickest. Well, this is the mathematical formula, and it might look a little complicated, but it's really not. Okay? And the way that we are going to calculate this, here's my hint. This left side of the equation, R1 over R2, what this is saying is this is the rate of gas 1 over the rate of gas 2. If you always put the lighter gas as gas 1, if you always put the smaller gas as gas 1, well then this is always going to be some number over 1, because this on the left side of the equation is just a ratio, right? If I'm half the size of someone else, mathematically maybe I move twice as fast as them. 2 over 1, so then the left side of my equation is just 2. Brilliant. But if you don't put the smaller gas as gas 1, well then you have to invert it. And then using the example we just mentioned, it would become 1 over 2. And I don't want to always have to worry about that. So I always make the smaller gas 1. And then that is equal to, notice that they flip it, it's 1 on the top on the left and 2 on the bottom on the left. But it's 2 on the top on the right and 1 on the bottom on the right. The square root of those 2 molar masses. And that is what we're going to look at the periodic table for. So let's look at some examples with this. Example 11. If equal amounts of helium and argon are placed in a porous container and allowed to escape, which gas will escape faster and how much faster? Well, we should be able to go ahead and determine who's going to escape faster, but we will mathematically calculate it here in just a moment. But if we look at the periodic table, helium is certainly smaller than argon. Helium is number 2 on the periodic table. Look at his molar mass. much smaller than argon, which means we're going to make helium gas 1 and argon is going to be gas 2. So let's solve that on the board now.
Next, we will be doing our Graham's Law examples. Keep in mind, it is R1 over R2. However, if you always make gas number 1 the lighter gas, the smaller gas, which you are always able to do if you manipulate the equation properly, well then this will just become one number on the left as opposed to a fraction. So our first example reads, if equal amounts of helium and argon are placed in a porous container and allowed to escape, which gas will escape faster and how much faster? All right, so our two elements involved in this equation are helium and argon, both of which are noble gases. Helium's molar mass is right at 4. And argon's is 39.95 or so. Not exact, but it'll do the trick for what we need here. So which of these gases is going to escape whatever container they're in faster? Well, it must be the lighter mass gas. Helium is going to escape faster. The smaller you are, the quicker you move. Which means helium wants to be gas 1 here. Which means, if we set this up correctly, the ratio of helium's speed of escape versus argon's is simply going to be our answer. If we put helium on top, then the number that we get in our calculator once we plug in the following numbers we're going to talk about here in a second, we get our answer. Okay? So R is equal to, and the reason why we're able to do that is because the question is saying how much faster, how many times faster will helium escape the container than argon? Well, next, the right side of the equation is the molar mass of the heavier gas over the molar mass of helium. So it should always be a bigger number on top of a smaller number. And the molar masses that we just got from the periodic table, argon's is on top, 39.95 over 4. And so we plug and chug into the square root. 39.95 divided by 4, and we're going to square root that number. And the number we get, and there's not really sig figs to go off of because you're not actually starting out with a numerical measurement here, and so we're just going to give it a couple decimal places. Helium is going to escape 3.16 times faster. Like so. Once again, the reason why this number, we can just leave it by itself, because if helium is escaping 3.16 times faster than argon, well then essentially what's occurring is this is the left side of your equation. It's 3.16 over 1, which is just going to simplify to 3.16. That is why I strongly, strongly encourage you to always make the lighter gas gas 1. If you don't, then you have to invert your answer at the end. That's annoying.
Example 12, what is the molecular weight, aka the molar mass of a gas which diffuses 1/50th as fast as hydrogen? Notice the language here. Diffuses 1/50th as fast as hydrogen, which means it is moving more slowly than hydrogen, which means hydrogen is, of course, the smaller gas, which means, if I look at my original equation, I want to make R1 the rate in which hydrogen is escaping. Well, if this gas is moving 1/50th the speed of hydrogen, if we flip it, R1 would be 50 and R2 would be 1. Therefore, the left side of my equation is simply 50. And then the problem becomes much more simple to solve. Solving it on the board now.
Example 12, what is the molecular weight of a gas which diffuses 1/50th as fast as hydrogen? The language in this question is a little different than the previous one. And we are going to manipulate it a little bit to make it look like the previous one. It diffuses 1/50th as fast as hydrogen, which tells you that it is slower. It tells you that it is the bigger gas, which means its molar mass is certainly going to be heavier than hydrogen. So what we are going to do is we're going to make that R2. And if we flip it, if this gas is escaping 1/50th the speed of hydrogen, well then that means that hydrogen is 50 times faster. So 50 is the left side of our equation. And that is going to be equal to the molar mass of our mystery gas X over the molar mass of not just hydrogen, but H2. Do recall that hydrogen is a diatomic element, a Brinkelhoff gas, if you will. And so now we can fill in the numbers that we do have, and what we do have is the molar mass of H2. And that is simply going to be 2 times the mass that you see of hydrogen on the periodic table, which is 2.02 or so. And now this is simple algebra, simply to solve for the molar mass of our mystery gas X. So what we're going to do is we're going to square both sides. That's the way that we're going to get rid of this square root, like so. And so a lot of you could probably do that in your head. We got 2,500 is equal to molar mass of mystery gas X over 2.02. How are you going to solve for X? Well, all you got to do is multiply both sides by 2.02. Right? Probably do a little bit of this in your head as well. I'm going to do this just to be safe and not look like a fool on this video. We get 5,050 equals the molar mass of mystery gas X. It's not telling you to identify it. How on earth would you identify something that is apparently 5,050 grams per mole? That is an exorbitantly thick with 3 C's and 2 Q's gas that we are looking at here.
In our last Graham's law example here that we are going to mathematically calculate, what is the identity of a gas if hydrogen diffuses 3.72 times faster than it? So we're going to solve for the molar mass, and then we are going to use the molar mass to actually determine the identity of our element or substance, compound, whatever it is. It's very hard to ask you to identify a compound because different elements can get together in different ratios and possibly come to this very similar molar masses. And so typically when they ask you a question like this, it's most likely going to be an element.
Our final Graham's law example is asking us to identify a mystery gas. What is the identity of a gas if hydrogen diffuses 3.72 times faster than it? Hydrogen is faster than whatever gas we are concerned with here, which means the left side of our equation is simply 3.72. And that is going to be equal to the square root of the molar mass of mystery gas X over the molar mass of hydrogen, which we just utilized, is 2.02, because it's not just H, it's H2, it's a diatomic element. Well, we're going to solve for X, and then we're going to see where we're going to go from there. Square both sides. This one I cannot do in my head, 3.72 squared. And we get 13.84 or so. Oops. Is equal to the molar mass of gas X over 2.02. So we're going to multiply both sides by 2.02. And just to be safe, our answer we get is 27.95 is equal to the molar mass of gas X. Well, how do you think you would identify this element? Well, this is the molar mass, and the molar mass of a substance we can find on the periodic table. And so you should be going to your periodic table. Keep in mind, this unit is gases, so the element that you are identifying must be a gas, which means it should be the color red if you've got a color-coded periodic table, yeah? So we're looking for gases that roughly have the molar mass of about 28 or so. You're looking, and oh my goodness. There isn't an element that has a mass that's especially close to 28. What on earth are we dealing with? Well, what did you have to do to this guy right here? Why is it 2.02? Why isn't hydrogen 1.01? It's because it is a diatomic element. Well, what if this is also a diatomic element? Maybe. So here's a little hint. If the number you get at the end doesn't exactly match up with an element on the periodic table, you either A, did it wrong, or it's a diatomic element. And if it is a diatomic element, simply divide it by 2. And so this is roughly 14 or so. And voila, you should see a gas that has a mass of 14 grams per mole. The element that we are dealing with here, the gas that we are dealing with here, is nitrogen gas, N2. However, if that doesn't work, well then you definitely did something wrong. So little hint, if you're looking to identify an element, you don't get a number that appears on the periodic table, try dividing it by 2 and see if something appears.
Example 14 is a purely conceptual question. It's still Graham's law, but purely conceptual. There shouldn't be any math we actually have to do. Two gases are placed in a tube and allowed to diffuse, meaning they're going to spread out, move through the tube essentially. The first one has a molar mass of 102 grams per mole and is placed in the left side of the container. And the second one has a molar mass of 166 grams per mole and is placed in the right side of the container. Roughly where will these gases mix together? And we've got all the variants of the tube, right? At either end, at the dead center, or a little bit towards this way, or a little bit towards that way. Well, conceptually, do we really think that they're going to meet at the far extremes? These gases are going to move. When they're put in the container, they're going to move. Do you really think it's going to be the far left or the far right? Those would really stick out to me if I were, a kid taking a test. But now let's discuss it using Graham's law, right? The lighter you are, the faster you move. So that's the critical concept here. The lighter you are, the faster you move. We've got our first gas, which has a mass of 102 that was placed on the left, and our second gas, which has a mass of 166 that was placed on the right. This 102 is going to move faster than the 166, right? That's Graham's law at work, which means the gas that is put into the left side is going to move faster. So now let's consider this tube. Let's say these two gases were in a race to meet at the middle. Who is going to get there first? Well, it's the lighter one, the one that's moving faster. But that's not when the race stops. It stops when they meet each other. And so because this one that was placed on the left side is going to get to the middle first, it's also going to reach a little bit past that, which means it would be the right side of the container, but maybe a little towards the center. It wouldn't be the far right, but I think the best answer here would be D. Right side of the container, but towards the center. And our last topic of the day is a brief review on gas stoichiometry. If you can recall, we actually did gas stoichiometry in the actual unit for Stoich. The only problem is we were always at STP. We were always at standard temperature and pressure. Well, now that we know a whole heck of a lot more about gases, we can expand the scope of our stoichiometry. We aren't always at standard temperature and pressure. Sometimes our temperature is higher or lower. Sometimes our pressure is higher or lower. However, if they don't mention anything about temperature and pressure, like in these next couple of examples, we're just going to assume it's at STP and keep it simple like we used to. But a little review is always handy. So we're going to always start with our balanced chemical equation. Okay? Very, very common reaction. Zinc plus hydrochloric acid makes zinc chloride plus hydrogen gas. And we are going to solve the examples in front of you. So look to the board.
We're now going to do example problems of gas stoichiometry. First thing that you need in any Stoich problem is you've got to have a balanced chemical equation. So before we even read the problem, we've got our equation. Zinc plus hydrochloric acid makes zinc chloride and hydrogen gas. We got to balance it. If we don't balance it, like a 95% chance we're going to get it wrong. All we need to balance it, though, is a 2 in front of the acid. Now we read our problem. How many liters of hydrogen gas can be produced from 22.6 grams of zinc? Notice there is no mention of temperature or pressure, which means we are going to simply assume that this is at STP. And that's very, very, very critical to how we're going to solve this. If it's at STP, then it's just like we solved these problems way back when, because 1 mole of any gas will always occupy 22.4 liters at STP. But as soon as you start changing the temperature and pressure, that's no longer the case. So the question is, how many liters of hydrogen gas can be produced from 22.6 grams of zinc? We're starting with grams of zinc, and we are converting to liters of hydrogen gas. Well, this is simply a 3-step problem, but I can't go from grams of zinc to liters of hydrogen without first being in moles. Moles is the universal language of chemistry. So what do I need to do? Well, grams of zinc is not my answer, so I send it to the bottom. Got to cancel it out. And it's not liters of hydrogen that goes on top, but it is mole of zinc. Well, where am I going to get these values? I don't know how many moles are in 22.6 grams, but I do know how to determine how many grams are in 1 mole of anything, and that is equivalent to the molar mass that we find on the periodic table. Molar mass of zinc is 65.39 grams. Next, we're going to go from moles of zinc to the substance that we want to end with, which is hydrogen, but we can't go to liters right away. We must be in moles. For every 1 mole of zinc, there is 1 mole of H2. Where did I get those values? Well, remember, whenever you're going from one substance to another, where's the only place you can find both of these in such close proximity? It is the balanced chemical equation. And when we balance it, we are providing the mole ratio. This is stating for every 1 mole of zinc and 2 moles of acid, I can make 1 mole of zinc chloride and 1 mole of hydrogen gas. So that's why we have these 2 ones here. Lastly, we're going to convert from moles of H2 to liters of H2 by sending 1 mole to the bottom. And because we are at STP, 1 mole of H2 will always occupy 22.4 liters. So now simply multiply by the top, divide by the bottom. Feel free to ignore the ones that are written. So we get 22.6 times 22.4 divided by 65.39. It doesn't matter what order you do that in. We started with 3 sig figs. We need to end with 3 sig figs, which means our answer is 7.74 liters of H2. The next example reads, how many grams of hydrochloric acid are necessary in order to produce 36.0 liters of hydrogen gas? Well, same 3-step setup. It doesn't mention temperature or pressure, so we're going to assume that we are at STP. So this should just be a simple stoichiometry problem. We are starting with 36.0 liters of H2, and we are going to convert to grams of HCl, like so. 3 steps, exact opposite of what we just did. Liters needs to be converted to moles, so we're going to send liters to the bottom. Mole goes up top. And in 1 mole of any gas at STP, there's 22.4 liters. Next, we're going to convert from moles of H2 to moles of HCl. Keep in mind, look at the balanced coefficients to get your mole ratio there. So, for every 1 mole of H2, since that's going to the bottom, there are 2 moles of HCl. Where did I get that 2? It is the coefficient of HCl in the equation. Next, we need to find out how many grams of HCl are in 1 mole of HCl. There's no point in bringing this 2 down here when the periodic table already calculates everything for you in terms of 1 mole. So what's the point of putting twice as much work on you? So we need to find out how much 1 mole weighs, which means we need to add up these 2 elements on the periodic table. Hydrogen has a mass of 1.01. Chlorine has a mass of 35.45. Add that together, and we get 36.46 grams per mole. So that's going to go right here. Now we're good to go. Multiply by the top, divide by the bottom. 36 divided by 22.4 times 2 times 36.46. We started with 3 sig figs, so we're going to end with 3 sig figs. It would require 117 grams of HCl to produce that amount of hydrogen gas.
And our final problem of the day, Stoich, but using gas laws. So this is the examples that I was talking about in the last clip, where we are not at standard temperature and pressure. We have the exact same equation, unbalanced still. Zinc plus hydrochloric acid makes zinc chloride and hydrogen gas. If 26.8 grams of zinc is reacted, what volume of gas will be produced at a pressure of 0.888 atm and a temperature of 27 degrees Celsius? What are we going to do? Well, first of all, we need to determine what the product is. What volume of gas? Well, which of these 2 is going to be a gas? Well, it's certainly going to be the hydrogen gas. So that is what we're looking for. We are looking for volume, aka liters, of H2 that is produced. However, we can't just plug and chug 26.8 grams of zinc and solve for liters of H2 because our pressure is not 1 atm and our temperature is not 0 degrees Celsius. We are not at STP. So what we're going to do is a 2-step process. We are going to utilize Stoich to solve for the one variable that we are missing that we would need for the gas law, for the ideal gas law, Pivnert. We are going to use 26.8 grams of zinc and convert that to not liters, but moles of H2. We're going to convert to moles of H2 because that is the missing variable we need for our equation Pivnert. We need the N. If we're solving for V, we need the N. We have the P, we have the T, of course we have R because it's a constant, never changes, so we need the N in order to solve for the V. So the stoich part of this problem is finding your N, and then you use the N in Pivnert to solve for the V. So that is how we're going to do it.
The last problem of the day, probably the most complicated, but it is utilizing everything that we already know thus far. It's going to be a combination of stoichiometry and utilizing Pivnert, the ideal gas law. So the question is, if 26.8 grams of zinc is reacted, what volume of gas will be produced at a pressure of 0.888 atm and a temperature of 27 degrees Celsius? This is, case in point, stoichiometry, but not at STP. Therefore, that 1 mole equals 22.4 liters no longer applies. So what we have to do is we have to find out how many moles of gas we're dealing with, then plug in the pressure and temperature that they provide in order to solve for the volume. So it's 2 steps. Find N, and then use N to plug into Pivnert. And so let's go ahead and keep track of our variables on the left over here. Like so. And now let's plug in what we already know. We have a pressure of 0.888 atm and a temperature of 27 degrees Celsius. We love it when they use that temperature because that equals a straight up 300 Kelvin. Very easy. So we're looking for volume in the end, but we first have to get N. We also already know R because that is a constant. We are going to utilize 0.0821 because the pressure that they gave us was an atm. Next, we started with 26.8 grams of zinc. And we need to find moles of H2. We are not going to solve for liters of H2 because that last step, when we convert from moles of H2 to liters of H2, it would not be accurate because we are not at STP. So we are simply going to convert to moles of H2 because remember, N is measured in moles. So grams of zinc has to go to the bottom. 1 mole goes up top. We've already said that 65.39 grams are in every mole of zinc. Next, we are going to relate zinc to hydrogen. There's 1 mole of reactant for every 1 mole of product. And boom. That should be all you need to get the unit that you're looking for. You're looking for moles of H2, so let's plug it in. 26.8 divided by 65.39. You don't want to round to your 3 sig figs just yet because we do have an extra step. You only want to round, ideally, in the final step when you're giving your final answer. So let's go ahead and give an unrounded answer. 0.4098486 blah yada yada moles of H2. And that's our N value there. So now let's plug it into Pivnert. We're looking for V. And if we're looking for V, we divide by pressure on both sides. Like so. Now your equation is manipulated. You have all of the variables that you need. So now let's plug and chug. And our answer is going to come out in liters. We're going to round this guy to 3 sig figs. Actually, sorry, 2 sig figs because our temperature was given in 2 sig figs. So our final answer is simply 11 liters of H2.